Okay, welcome folks. Today we're going to be talking about logarithms, the inverses of our exponential functions. Just to warm up, we're going to start by building a brief sketch of the function f of x equals 2 to the x. So remember that our input x is going to go up in the exponent here. So just take a moment, pause the video, draw like a real basic sketch. You could include maybe 3 points or something on your graph. If you are feeling a little bit wobbly about how to get started, remember that you can always build yourself a table. So for example, if we look at x equals -2, we have f of -2 is 2 to the -2. So that's going to be equal to 1/4. So just take a moment, build yourself a sketch, and then we will reconvene. Okay, so we should have a sketch that looks kind of like this. So its y-intercept is 0, 1. We can see that the domain is all real numbers. The range is 0 to infinity. Some of the other things we notice, as x gets big, our y values are getting big as well. And as x gets very negative, our y values are getting close to 0. We'll call this line that we're getting close to, which is the line y equals 0. We'll call this a horizontal asymptote. So our graph gets really close to this line. Okay, we see that this function is increasing, and it's invertible, right? For any y value, if we draw a horizontal line across, we will intersect our graph in either 0 places or 1 place. And so we're able to read off from our graph, given a y value, we're able to read off that x value that it came from. So for example, here, if we wanted to solve 2 to the x equals 4, so 2 to the what gives us 4, well, we can look here where our y value is equal to 4. And looking down on our graph, we see that this happens where x equals 2. So we have this point 2, 4 on our graph. So 2 to the x is going to be equal to 2 squared, and so x is equal to 2. Similarly, we have 2 to the x equals 16. So 16 is 2 to the 4th. There's only one x value that's going to satisfy this equality. And so we say, okay, x must be equal to 4. If we wanted to solve 2 to the x equals 1/2, we can read this off of our graph, where y equals 1/2. This is at x equals -1. And we can also read it by taking 1/2 and then rewriting it in terms of rewriting it so that we have a base 2 instead of 1/2. So comparing 2 to the x equals 2 to the -1, we see that x is -1. Now, if we want to solve 2 to the x equals 3, there is certainly a place on our graph that satisfies this. We can go to y equals 3 here, and looking, we see that there's definitely some place in this, some x value here, for which there will be a solution. The best way we have to write this is just saying x is the inverse of f evaluated at 3. So that the inverse function is going to be called the logarithm. So we're going to write the log base 2 of x for the inverse. And let's just take a moment to try sketching our inverse. So there are sort of two major techniques for sketching our inverse. So one of them is just to reverse all of your XY pairs. So if we have, we had that -2, f of -2 was equal to a fourth. So this is going to have, let me write my y log base 2 of y pairs. Well, we had 1/4 is going to give us -2. 1/2 is going to give us -1. 1 is going to give us 0. 2 is going to give us 1. 4 is going to give us 2. So we're just flipping the x and y pairs. The other way we could think about this was imagining this line y equals x and reflecting our graph across it. Okay, so let's take a moment, pause the video, try and draw your sketch, and then we'll circle back together. Okay, so we have a plot that looks a lot like this. So this time we have no y-intercept, but we have an x-intercept. The x-intercept where we cross the x-axis is always going to be 1, 0 here. Let's label a couple of other points here. We have 2, 1. We have 1/2 -1. Okay, we see this function is also increasing. This this horizontal asymptote that we were close to in 2 to the x, when we are swapping our x and y values, that line that we're getting close to now becomes x equals 0. And so this is called a vertical asymptote because it's a vertical line. Okay, the domain and the range flip in the inverse. So the inputs of the inverse are the outputs of the original function. So the domain here we see from our graph is 0 to infinity, and our range is now -infinity to infinity. All right. Great. And so this is our inverse function. Fabulous.